Hey everybody, welcome to what will be our final lesson for Organic Chemistry 1. This is a lesson that's going to pick up right where we had left off in class on that Tuesday, where we were beginning to talk about the halogens. Now, this video is probably going to be a little bit longer than 30 minutes, I suspect, so you should feel free to watch it in a couple of chunks if you want. Also, the content that I'm going to cover is coming from sections 19.9 to 19.12 of the textbook. So you're also more than welcome to just flip through those portions of the textbook on your own. Hopefully you have it with you at home. Flip through those portions of the textbook at your own pace, and then come back to this video and maybe watch the bits and pieces that you might need some clarification on. Okay, so here we go. So we were talking about electron donating activating groups and electron withdrawing deactivating groups, and we were just talking about how halogens are kind of in between. It turns out that halogens are deactivating groups because they do pull electron density away from the benzene ring, as the structure on the right here shows. We have the benzene ring with the chlorine on it, and of course chlorine is more electronegative than carbon, so the electron density gets pulled away from the benzene ring, so the benzene ring is less nucleophilic. So in that sense it is deactivating, but it is also a ortho-para director, because we can imagine that there are in fact lone pairs on the chlorine that will be pushed into the benzene ring that ultimately put negative charge at the ortho position and eventually negative charge down here at the para position. So they are deactivating groups, halogens, but they are ortho-para directing. Okay, so we can see this a little bit more clearly on this next slide, where we go through and we look at the electrophilic addition at the different locations at the ortho, meta, and para positions. And we can see how in the ortho attack and in the para attack, we have a fourth additional resonance structure that's available. Now, we should notice, right, this resonance structure, I'll go ahead and zoom in at the top right, this resonance structure isn't terribly good in that it has a positive formal charge on the more electronegative chlorine atom. So that's typically not what we want. So it's certainly a secondary resonance structure in terms of relative stability, but it is certainly worth mentioning, and it does add to the overall set of stabilizing resonance structures. All right, so again, a halogen is a little bit of an outlier. It's deactivating like a nitro group, but it is ortho-para directing like a methyl group. Okay, so let's start looking at the different groups in some more detail. I'm going to start with the activators and work my way over to the deactivators. We're going to kind of rank them in terms of how strongly, moderately, weakly they will activate and deactivate. So thinking about the activators first. So these are the strong activators that we're going to list here. And the question here is, what makes them strong? And what makes every single one of these substituents, the alcohol substituent, the amine substituent, the different versions of amine substituents, all of these are strongly activating because every single one of them has a lone pair of electrons on an atom immediately outside the benzene ring. And so here I'll zero in on the alcohol group for a moment. So what that allows us to do then is have resonance structures where the lone pair can be pushed into the benzene ring, and we eventually get that negative formal charge on the ortho position. And of course we can resonate that around until we have the negative charge on the para position. So strong activating groups have lone pairs that can readily resonate into the ring. What makes something a moderate activator? Well, if you look at the structures we have here, they too, down below, they too also have lone pairs on an atom just outside the benzene ring. So that's what will make them activators. But those lone pairs can also be pushed in the other direction. So instead of the lone pairs here on this oxygen only going in that direction, we could imagine that the lone pairs could actually be forced the other way. So this lone pair could go towards the external carbon of the overall ester functional group, and that would push those electrons up there, and so eventually I would get a negative formal charge right there. So moderate activators also will have lone pairs available outside the benzene ring, but instead of only being able to resonate towards the ring, they can be resonated away from the ring. So only going in, they can also go out. All right, so that's what will make something both a strong and moderate activating group. Again, going to be preferentially forming the ortho and para substituent. In our catalog of only being moderate activators, so these groups right here, they were moderate. All right, weak activators. So now we're back to looking at things we started this conversation with, things like a methyl group or an ethyl group. So you'll notice here, there are no lone pairs on these branches that can be pushed into the benzene ring. The only way that these are activators is, as we discussed in class, these alkane chains, they have a lot more electron density than just the simple hydrogen. So the extra electron density that these groups can bring to the benzene ring by way of induction, not actually a resonance effect, but only an inductive effect, that's what can amp up the nucleophilicity of the benzene ring only in a slight way, only in a probably even less than moderate way. Okay? And so that takes us then all the way from strong activators down to weak activators. Let's start building up then in the other direction. Let's start with our weak deactivators. And the perfect place to begin here would be those halogens we were just talking about a couple of minutes ago. All right, so now we know that halogens are deactivators because of their ability to pull the electron density away from the benzene ring. But we also know that they prefer to substitute at the ortho and para positions because, again, we can push the electrons in and get formal charges at the ortho and at the para positions. All right, so that gets us then to the beginning of the deactivators. Let's keep talking this through and start talking about some moderate groups. They showed up active deactivators. So here are different groups that we would refer to as moderate deactivators. And what's going to make these moderately deactivating is that they are going to tend to pull electron density away from the benzene ring. More importantly, there's really no clear resonance structure that allows us to start to push electron density towards the benzene ring. So let me zero in on, say, the ester here on the right. Of course, this ester has some lone pair electrons on it, but there's no way to get these lone pairs, or even these lone pairs, there's no way to get them towards the benzene ring. And of course, oxygen atoms are more electronegative than carbon, and so there's a general tendency, inductively again, to pull the electron density away from the benzene ring. And if we draw any kind of resonance structure, I'll slide over and take a look at, say, this carboxylic acid group. Any resonance structure that we could draw would actually be taking electron density further away from the benzene ring. So for example, I could take the double bond between the C double bond O, and I could push the double bond up towards the oxygen, ultimately making that oxygen have a formal negative charge. And so clearly we're starting to push the electron density away from the benzene ring. Okay, so now let's talk about things that would be considered then strong deactivators down here on the bottom. So we've talked a lot about nitro groups, right? And I'll just draw a nitro group out in a little bit more detail down here. So we could have N, and then we could have the O, we could have another O, and we could, depending upon how we want to count our valence electrons, we would have something that maybe looks like this. And so if you take a look here, this oxygen on the left is going to have a negative formal charge, and the nitrogen here is going to have a positive formal charge. So not only are nitrogen and oxygen more electronegative than carbon, so there's an inductive effect pulling electron density away from the benzene ring, the atom that is attached to the benzene ring, this nitrogen here, has that positive formal charge. So it's really good at pulling electron density out of the benzene ring, thus making it a weaker nucleophile, thus making it not so good at doing the electrophilic aromatic substitution. All right, we see the same effect for this cationic nitrogen here, this sort of ammonium substituent on the benzene ring, right? That nitrogen right there is clearly positively charged, so we have that issue there. And then we could have something like this group here, where, of course, X is going to be a halogen, so now we have a carbon that's going to have very little electron density around it because of all the polarity that's happening with the halogens pulling electron density away from that carbon. So that carbon now has a noticeable pseudo-positive charge. Maybe we can't call it truly positively charged, but boy, is it going to have a strong pseudo-positive charge. So it's going to come darn close to behaving almost identically to this truly cationic nitrogen. All right, so the deactivators, again, they're going to be pulling electron density away from the benzene ring, okay? All right, so that in a nutshell then are the different kinds of substituents that could go on a benzene ring to activate it and favor the ortho-para positions, deactivate it, favor the meta positions, and then of course we have halogens that are ortho-para directing but also deactivators. Remember my acronyms in class: AOP, activator ortho-para, DM, deactivator meta, and then we had HDOP, halogen deactivator ortho-para directing. So now what we're going to get into is we're going to look at benzene rings that now will have more than one substituent on it. What happens if we start having multiple substituents? And so we've got to kind of consider the effect that's happening. But if we go back and take a look, these before we get into that, let's just talk one more time here about determining the directing effects of the substituent. So you've got to identify whether your substituent is activating or if it's deactivating. So the first thing is to identify the substituent. Can anybody name this functional group here? What kind of a substituent is that? If you said amide, you are correct. So amide groups, right, they will have, of course, a lone pair on the nitrogen, right? We're going to have that lone pair on the nitrogen. So you might begin to think, okay, well, that's going to make that a activating group. So this compound, this benzene with the amide group on it, the benzene with the amide on it, it's going to push things towards the ortho and the para positions. Now, you might be able to think, well, if we actually did some chemistry, if I go ahead and tried to add, say, a nitro group to this, right, through our nitric acid and sulfuric acid, would I end up preferring the ortho position or would I prefer the para position? And this, of course, gets into the conversation about the fact that this is going to be a pretty big group. So it's going to cause steric interference. So I strongly suspect that we're going to see a great percentage of the para substituent being filled if I put that nitro there on the para position instead of any available ortho position. Okay, so let's get into multiple substituents. So what we've got to do is talk about maybe possibly competing directional effects. So we have directing effects of the substituents, and sometimes these directional effects might complement each other. Sometimes they might compete against each other. So let's take a look at this example here. So I have toluene, a benzene ring with a methyl group on it, but then I have a nitro group there. So this is actually going to be called para-nitrotoluene is what I would call that. All right, can you understand why? Para-nitrotoluene. All right, so now we're going to do the substitution with bromine. So here's the question. Will the bromine atom, will it end up ortho to the methyl group or ortho to the nitro group? And what would the methyl group and the nitro groups say about that? So here's how I'm going to answer this. I'm going to circle the methyl group in blue, and we know that that methyl group is a mild activator, so it's going to push things ortho to it. Of course, it would like to also push things para to it, but that location's already taken, so we can't substitute there. Now, if we take a look at the nitro group is deactivating, and so it's going to want to push the incoming electrophile at the meta positions. And well, what do you notice? We have here a complementary effect. So the new product I'm going to make here, draw my benzene ring. We'll have the methyl group up here, para-nitro group, and so the bromine that's going to come in is going to want to be ortho to the methyl, meta to the nitro, and conveniently enough, it's the same spot, right? That kind of sounded like a song there for a second. Ortho to the methyl, meta to the nitro, and you end up in the same spot. So sometimes, as we see here, substituents can be complementary. So I suspect you'd get a pretty high yield of this. Let's see, what are we going to call this? We're going to call this orthobromo-para-nitrotoluene. And so I think we get a pretty good yield of that compound. Let's take a look at another example of multiple substituents. So here I have an alcohol group and a methyl group. Now, let's think this through. Let's, again, color code things. So here's our alcohol group. It's going to want to be, right, alcohols are strong activators. So it's going to push things to the ortho position and, of course, to the para position, but that's not available. And then the methyl group is going to want to push things to the ortho positions and to the para position, but of course that's unavailable. So now these two groups are actually not complementing each other. So we have to decide, okay, who's ultimately going to win? So I'll draw out the two possibilities here. So I have my benzene ring, I have the OH, I have the methyl, and so one possibility is I could put the nitro ortho to the OH group, and my other product possibility, I could put the nitro ortho to the methyl group. And so one of these is going to be the major product, one of them is going to be the minor product. And so which effect is going to win out here? Well, when you have activating groups, the major product is going to be the consequence of the stronger activating group. OH is a stronger activator than methyl, so the OH is going to have more to say about how this chemistry transpires. So our major product then in this comparison is going to be the one that has the nitro group ortho to the hydroxy group, the alcohol group, and we'll have a minor product where we nitrate in the ortho position relative to the methyl group. All right. Now, given that this position here is a meta to the OH, when I say minor, I suspect I'm talking truly minor, because that OH does not want the nitro group to go into the meta position. So I think we're going to have a noticeably major amount of the ortho relative to the alcohol group in our mixture here. Okay. So let's do a comparison here. So now we're going to get into some possible subtleties here. So we have now two similarly activating groups. I have an isopropyl group, this is called. Propane means 3 carbons. Iso means it's attached by the middle carbon. So it's called an isopropyl branch. And I have a methyl branch. And now they both activate in the same way, right? The isopropyl is going to want to activate ortho, and the methyl is going to want to activate ortho. And so we've got our two possibilities. We could nitrate relative, or add the nitro group relative to the ortho position of the methyl group, or ortho to the isopropyl group. Now, you might think, well, isopropyl has more electron density than methyl, so while they're both maybe only weak activators, maybe the isopropyl is a stronger weak activator. So then you might think maybe this is the way to go, all right? Or maybe you think, well, maybe there's really no difference, so maybe possibly I'm going to really end up getting a 50-50 mix, because whether we're isopropyl or methyl, maybe there's really no difference. Well, let's take a look and see what the outcome is. Before I go to the next slide to show you what the outcome is, try to draw the structure of something that you're pretty sure you would not see ever, okay? Which structure really has no chance of coming about, all right? And let's see, we will, oh, actually, I'm sorry, I'm getting myself confused. I'm going to rewind here. Let's go ahead and finish this one off because our next example is actually a completely different example. All right, so is this going to be a 50-50 mixture? I don't think so. I think the result we're going to get is going to end up being this guy here on the left, right? Because the nitro group, if it's there, it's only experiencing some steric interaction with the methyl group. Whereas if we put the nitro here, there's more steric interaction with that larger isopropyl group. All right, so I think we're going to want to go ortho to the smaller, weak activator. All right, so sorry about that. Let's go to the next slide where we actually bring in a slightly different version of the same kind of question. So here again we have isopropyl and methyl. So here's the isopropyl group, here's the methyl group. And so if we go ortho to the isopropyl, we could go here or here. And of course we could also go there if we want to be para to the isopropyl group. The methyl group is going to want to substitute here, here, and here. So the question is, which of these options are available? So essentially, I've pretty much put every single carbon, right? So this carbon is in play, this carbon is in play, that carbon is in play. The only carbon that's not really in play is this carbon right here because it's a meta to both the isopropyl and the methyl group. So it turns out that our major product is going to be the one that places the nitro group, as you see, right here in the ortho position relative to the methyl. Now that's nice because the methyl group is smaller than the isopropyl, so that creates less steric interaction. But bonus, this nitro location is also para relative to the isopropyl. So the isopropyl is happy to put the nitro para, and the methyl group is happy to put the nitro group ortho, and when it does so, it's giving us a result that has less steric interference. This compound here, right, that's a perfect possibility, right, because now you're ortho relative to isopropyl, you're para relative to the methyl, so that's a good choice. But of course, you're going to have larger steric interference between the larger isopropyl and the nitro group. So that's only going to be a minor product. What do you not see? Well, you might think that this is a pretty good choice down here. By putting the nitro there, we're ortho to the isopropyl and we're ortho to the methyl, right? So that's kind of like a double ortho. But of course the problem is major steric interaction. You've got the sterics with the isopropyl, you've got the sterics with the methyl, and so instead of only costing yourself one steric interaction or one steric interaction, this bottom structure costs you both steric interactions. So we're not going to observe that particular pattern of substitution. All right, so let's take a look at some more examples here of multiple substituents, right? What reagents might you use for the following reaction? So I would like to preferentially form the bromination of the benzene ring ortho relative to, this is going to be called a tertiary butyl group. There are 4 carbons, 1, 2, 3, 4. So that's a butane chain, and the way that it is arranged, because that's now a tertiary carbon, we call it a tertiary butyl group. Anyways, so this is going to be a weak activator, right? It's pushing electron density in towards the benzene ring, but I don't want to get any of the substituent, the bromine substituent on the para position. I want to eliminate that as a possibility. I want to try to get 100% yield of just the ortho bromine substitution. So the way that we do this in organic chemistry is we block the pathway to some likely reactive spots. And we often do this with sulfur groups, as you'll see in a minute. So here's kind of the logic of what we would try to do. I have my tertiary butyl, and I would try to install what we're calling a blocking group in that para position. If I can close that off, do the bromination, get the bromine where I want it, and of course I wouldn't want to get the bromine here, so I've got to make sure that whatever I have here is not as activating as the tertiary butyl group, because I would want to make sure that the bromine goes ortho to the tertiary butyl and not ortho to the blocking group. So I block the para position, right, close that off, brominate where I need to, where I want to on the ortho position, and then get rid of the blocking group. Now, if you go way back in the notes, if you go probably to one of the first handful of slides when we were talking about electrophilic aromatic substitution, we talked about a reaction called sulfonation. Sulfonation can help us out here. The electrophilic aromatic substitution involving sulfonation is reversible. If you go back in the notes, you will see an example where we take benzene, and if we use what we called fuming sulfuric acid, so you take sulfuric acid and you blow SO3 gas through it, so it's highly enriched in SO3, it's fuming sulfuric acid, you can sulfonate the benzene ring. If you expose the sulfonated benzene ring to a dilute solution of sulfuric acid, you can actually pop the sulfate group off and return back to the benzene. So things like these sulfate groups, they make good protecting groups. So what you can do is in the sequence down here below. You can take the tertiary butyl benzene, expose it to fuming H2SO4, and you will sulfonate in the para position. Why the para position and not the ortho position? You should know the answer to that by now. The answer is sterics. Right? This is a big tertiary butyl group. It's really going to close off access to the ortho positions relative to it, and it's going to open up the para position. So we can go ahead and sulfonate at the para position. And now the SO3 group, it has these oxygens on it, right? So that's actually going to result in the SO3 group being a bit of a deactivator. It's going to pull electron density away from the benzene ring. So the SO3H group is going to be a deactivator. The tertiary butyl group is going to be its typical activator. So this will want to push ortho. This will want to push meta. And so what do? You get the bromine right where you wanted it. You get it ortho relative to the tertiary butyl group and meta relative to the sulfonate group, which is exactly where you want it. Then you expose this product to dilute H2SO4, the sulfonated group comes off, and you have your target group. So sometimes chemists will do reactions in the anticipation of kind of undoing that reaction later on because they want to close down a particular pathway for a potential byproduct. Okay? These things are what chemists typically refer to as a blocking group. Sometimes they're called a protecting group, blocking or a protecting group. All right, so this has been a pretty long video. We've gone through quite a bit of stuff. I hope you've been able to get through all of this. Maybe with the help of previewing it a little bit in the textbook, the video hasn't been too much. And so let's get to one last slide where we kind of see the big picture of all of this chemistry that we've described in electrophilic aromatic substitution. So we can start with a benzene ring, and we can do 1, 2, 3, 4, 5, 6 kinds of reactions, right? We can halogenate, we can add a nitro group, we can sulfonate, we can alkylate, and we can acylate. So there are 6 synthetic chemistry steps that we've made available to us by way of electrophilic aromatic substitution. Then, from these particular products, we've seen a couple of examples of additional reactions we can do. We have the nitro group. These oxygens make the nitrogen have what we call a high oxidation state. We can reduce that oxidation state by exposing it to a combination of iron or zinc under acidic conditions to turn it into an amino group, right? So that's a reduction, to turn the nitro into an amino group. We also talked about in class how we could take the acylated benzene ring, right? We could go from this acylated group, and we could reduce it using what we called the Clemmensen reduction to make an alkyl group. And so that is a way of getting primary alkanes onto the benzene ring. On this slide, we see 2 other reactions. I'm not going to keep you responsible for those. Those are talked about in previous chapters in the textbook that we didn't cover, but these are other examples. This is an oxidation. This is another kind of a reaction that we're not going to worry about for now, but there's additional chemistry that we can do. All right, so that ends electrophilic aromatic substitution. All right, hopefully this helps you get through the rest of the notes. You should also make sure that you're wrapping up the notes from our other textbook, that Chem Activity 19. You want to make sure you're doing that, and hopefully you feel like you're in good shape for the take-home test. All right, and that's it, and I hope I'll see you soon.